Welcome back to another session on this course. And we have today on three-phase, we will talk about three-phase uncontrolled diode bridge rectifiers in this, and this is part of module A. And basically we are now in week 1 where we are going to talk more about the controlled and uncontrolled rectifiers. Um, so in the last class we had covered about the single phase rectifiers, diode bridge rectifiers, and today onwards we will study three phase uncontrolled rectifiers. Where do we use this? We use three-phase rectifiers to convert three-phase AC to DC when the power level is high. Generally, we use single-phase rectifiers when the power level is low, and three-phase when the power level is high. And these rectifiers are extensively in use for a variety of applications. Previously, historically, it was very popular for DC motor drives, where we wanted to have a DC voltage output, but it is not so popular for DC motor drives nowadays. But it actually is used very much in AC drives, for example induction motor drives, where you might recall that we use a rectifier at the front side to connect it to the AC grid, rectify that AC grid into a DC voltage which forms the DC link of the inverter, and this inverter is then used to drive the AC motor. So the front end part consists of this kind of a three-phase rectifier along with multi-pulse transformer arrangement, and this is where this kind of three-phase diode rectifiers are used throughout the world in many applications, AC drives or some other applications also, very prominent converter. So basically this is kind of the lecture that we will cover is a basic recap of the first undergraduate level on power electronics, and as we have understood that a half or a full wave rectifier converts the three-phase AC into a fixed DC which will be fed into the load. So if we try to analyze the operation of the converter, then we see here that we can analyze with the help of three-phase half wave rectifier, and where I have shown this half wave. The half wave is nothing but a combination of the AC source and a rectifier and a diode, right? So this arrangement is the half wave rectifier, right? And suppose we have this kind of a voltage VA, VB and VC, which are sinusoidal quantities which represent the grid voltages. The first thing to understand is which diodes will conduct at what time, because you can see here there are three diodes. They are connected to the three phases and the load is connected here. So which diode will conduct? And in order to understand this, we have to see that out of the three phases, okay, because this is a three-phase sinusoidal grid, and the phase having the highest instantaneous voltage, okay, the phase out of the three, the one phase which is having the highest instantaneous voltage, that will force the diode in that phase to conduct. Okay, so you can see here there are three phases here, VA, VB and VC, out of which, for example, if we take this interval here, okay, in this interval, out of VA, VB, VC, VA is maximum, okay, during this interval, and therefore this diode which is connected to VA, which means this line here, this will be conducting and the circuit will be completed like this. Okay, at this point. Again, at time t2, what we find is that, so at this time t2, we find that VB becomes more than VA, the instantaneous voltage, and therefore this diode D2 will start to conduct, okay, and current will commutate or transfer from A phase to B phase, right? So how does the current transfer from A phase to B phase? Again, we can recall the way we had discussed it earlier, is that at this moment, okay, this moment, if you consider carefully, momentarily you can assume, momentarily, okay, that you can assume that both D1 and D2, they are conducting momentarily, okay, and then what will happen is, if both D1 and D2 are conducting, then this VB voltage will come here. So this point's voltage, so the, if D2 is conducting, VB will come here, right? And at this point, just after this point, okay, what happens is the VBA voltage, so here just after this point, the VBA voltage, that voltage VBA, right, is greater than 0, or otherwise we can say that VAB voltage is less than 0, okay, right at this point, okay, just at this point, after this, the VAB voltage becomes less than 0, and that will cause this D1 to be reverse biased, right? Momentarily, if you assume at the transition both the diodes are conducting, then the point V points B volt, this point's voltage will become VB, and then it will immediately turn off D1, okay, and that is how the current which was earlier flowing through D1 will now shift to D2, okay, and this is the natural commutation of the current from A phase to B phase, okay, and that is how D1 will turn off, right? So this is how the commutation will happen. It will also happen in this interval, like this, right? Now what is the output voltage waveform? The output voltage waveform is, as has been shown here, basically it is nothing but the envelope, okay, this is the envelope of the, this is the A phase, this is the B phase, this is a C phase, and again A phase, B phase, and C phase. It will the envelope, the outer envelope of this will be seen at the output voltage which is present across the load. So that's what here is written. The output voltage is an envelope of the maximum of the three phases, right? And this will repeat every 1/3 of the time period, okay? So this is basically T by 3 here. This distance is T by 3. So therefore it is now possible for us to actually find out the average voltage, right? So as you can see here, we have written V0 or V output follows VA from T by 12 to 5T by 12. So this is like T by 12 and this is 5T by 12, okay. So pi by, so T by 12 means this is pi by 6, so this is pi by 6 to 5 pi by 6 here. Basically this is about this is like the conduction period is 2 pi by 3 or 120 degree, right? So therefore VA will be so V0 follows VA from pi by 6 to 5 pi by 6. So therefore we can find out what is the average voltage. So the average voltage, because it is getting repeated, so we will write down the equation of VA and we will integrate from pi by 6 to 5 pi by 6, because our the V0 follows VA from pi by 6 to 5 pi by 6. So our integration is also from pi by 6 to 5 pi by 6, and then it repeats, and this is the Vs sine omega t, that is the equation of VA, and the time period here is 2 by 3, okay. We will the average, the division will be 1 by 2 pi 3 or 1 by yeah. So therefore the, if you do this calculation, the average output voltage will be coming out something like this, which is this voltage here. Okay, so this is the V0 average. Fine. So this much of voltage is obtained here in a three-phase half-wave rectifier. This can also be extended theoretically to a constant current load. Although we do not use this kind of half-wave rectifiers, okay, we use a full-wave rectifier, which we will see in a few slides later. But theoretically, we can say that we can also use a constant current load in this case. And when there is a constant current load, which was like constant current load means something like a DC motor. Okay, so if we have a DC motor, the winding inductance is so large that the armature current can be thought of like a constant current, ripple free and in the continuous conduction mode. So then this so then the waveform is what has been shown here. One of the things is that, again, as I told you, how the current commutates from D1 to D2 when VBA is positive. So here we have shown this VAB voltage, right? And the VAB voltage goes negative here. Okay, so which means VBA becomes positive. So at this point, VBA becomes greater than 0 at this point here. Okay, so therefore we can say that the output voltage now follows this envelope here. Okay, something like this. Now what happens here is that if you see the input current waveform, okay, or the source current waveform, so this is the grid here. Remember, this is the grid, okay, three-phase grid, and the current drawn from the grid is given by this IA, IB and IC. And you can see here that IA is conducting only during this, A phase is conducting only during this period where D1 is conducting, and B phase is conducting only during this period, and C phase is conducting during this period. And therefore what happens here is that the IA current is something like this waveform here. Okay, so in this case, with a constant current load, we see that the current, source current, is highly non-sinusoidal. It is non-sinusoidal, and as I am telling you, we will see this phenomenon happening repeatedly, that for this kind of rectifiers, whether it is controlled or uncontrolled, okay, controlled rectifier means thyristor rectifier, this is a phenomenon, this will go on happening, that the source current will become very non-sinusoidal, okay, very much non-sinusoidal. And this is a very big problem for the diode rectifiers or even thyristor rectifiers at a later stage, where they will not be able to meet the power quality standards as expected or as demanded by the grid. This is one of the biggest drawback of this kind of rectifiers, although it is very simple in its operation. So here you can see that the current IA is very much like a square wave or quasi square wave. Okay, now what will happen if you use a capacitive load? Okay, now we see a capacitive load again. So in this case we have this C and R here. So what happens here, we have already discussed this in the last lecture, lecture 2, how it behaves with a capacitor. So what happens here is that the capacitor charges during a certain period and then it discharges in this period. Okay, so the capacitor charges and discharges continuously, and when it charges, basically the source actually charges this capacitor up, and when it discharges through the load. Okay, and in this way, through this constant charge discharge, the capacitor maintains a DC voltage, and therefore that voltage comes across the load. Okay, so in this case the capacitor, this is the charging period of the capacitor, and this is the discharging period of the capacitor. So between t equal to t by 4 and t equal to t1 plus n, the So when the capacitor is discharging, so from here to here, okay, so what happens is, so this voltage, so this is the V0 voltage, as you can see here, this is the output voltage, and this point's voltage is Vs. Okay, this point's voltage is Vs. So when it is discharging, that is during this period of discharging, the capacitor, the output voltage V0 is Vs into e to the power minus t by Rc, because this is discharging through this Rc time constant. So this is the R here. Okay, so it through this through this Rc circuit, the this is the Vs discharging, Vs e to the power t minus Rc. This is the place where it is discharging during this point. Okay, and during this point here, when it is charging, so the one of the diodes will be conducting, and then it will follow the input voltage. Okay, during the charging period. Okay, so this we have already discussed in lecture 2, so you can just have a look into it. So the peak to peak ripple voltage, therefore on the output VR peak to peak is, what is it, Vs. So this point's voltage is Vs here, Vs minus Vs into e to the power minus t by Rc. Okay, so e to the power minus t2, so this time instant is t2. Okay, so therefore this is VR peak to peak is Vs minus Vs e to the power minus t2 by Rc. And if I assume that the Rc time constant is quite large, then I can approximate this e to the power x as 1 minus x. So basically e to the power x is 1 plus x square by 2 factorial, like that. But I can make a first approximation, and I can write it like this way. And so VR peak to peak is something like this, okay, which is nothing but Vs into T2 by Rc. Right, now if the charging time, charging time is very small, so if the charging time is much less than the discharging time, which is mostly the case, because when the time constant is large, this happens, we can also say that T2 is almost equal to T by 3, which means that this T2 time period here, okay, it is almost covering this whole time period T by 3, okay, almost. So this is the time period T by 3. So this T2 here is covering almost the whole of that T by 3 time period. So we can write this T2 equal to T by 3, and hence VR peak to peak is Vs into T by Rc, coming from this one. Okay, now so this was something which is useful for understanding. However, we do not use the half wave rectifiers, primarily because of the reason that we are only using the positive half of the AC voltage. If we want to use both the positive and the negative half of the AC voltage, then we use something called as a bridge rectifier. Okay, and the bridge rectifier is given by this circuit here. Okay, and the diodes are, you can see here, the diodes are like this. The AC grid is here and the load is here. The diodes are numbered in this fashion, 1 3 5 6 4 2. The reason is the way they conduct. Okay, the way they conduct in a sequence. Okay, that is how these diodes are drawn. Okay, so the three-phase bridge rectifier is a more common circuit for high power application. And so in this case, what happens, the way we analyze is that we have like we can think of this thing as a positive group and this thing as a negative group. So this is where there is a positive group here, you can see, and there is a negative group. Okay, so this is how the analysis becomes much more simpler, because we have already analyzed the half wave rectifier, and here we can see that out of 135, so this is producing the positive V01 voltage, and here this is producing the V02 voltage. Okay, So there is a positive diode group and there is a negative diode group, okay, with a positive one has a common cathode and negative has a common anode. So this connections, okay, positive common cathode and common anode connections. So this will produce something like this kind of a output voltage. So therefore it becomes simpler for us to actually analyze, okay. So for example, we can say that this positive group here will produce this kind of a voltage, which we have already analyzed, because this is following the envelope of the maximum, this is following this envelope here, okay. So this envelope is basically followed here for the positive group. Similarly, the negative envelope, so you can see here, so the negative group, okay, so the negative group will follow this envelope here and this will come here, okay, this is what is going to come here, right, okay. So this is basically V02. So then we have this V01 and V02 we are obtaining, okay, by tracking the positive envelope and the negative envelope, right. So when you do this one, how much is the V0, the output voltage? The output voltage, if you just see here, it is nothing but V01 minus V02, okay. VO1 minus VO2 is the V output voltage. So so therefore we can actually get this kind of an output voltage here, okay. So yeah, so the output voltage VO is VO1 minus VO2, and so this voltage is basically a 6 pulse waveform, okay, because now we have 6 lobes, okay, there are 6 lobes here, okay, here you can see there are 6 lobes in one cycle. So that is called a 6 pulse waveform, and each lobe is having a width of 60 degrees, right. Here also you can see that this voltage peak is Vs on VO1 and this voltage peak is minus Vs on VO2, but this peak is √3 Vs. Basically it is following the line voltage, right? Because what is the reason? Because one diode from the positive diode group and any one diode from the negative diode group is conducting. So for example, the circuit can be thought of like this way. So at one point, okay, this is the way the circuit is getting complete, and therefore you can understand here that VAN minus VN, so here the VAB voltage is coming at this point when D1 and D4 are conducting, okay. So this is the VAB voltage, and therefore since VAB, the line voltage is appearing across the load, so therefore the peak voltage is √3 times Vs, okay. So this is appearing across the load, okay. Yeah, so there are actually 6 pairs of conducting diodes. So you can see here, say 1 and 6 conducting here, then 3 and 6 conducting here, then 3 and 2. So here 1 plus 6, here 3 plus 6, here 2 plus 3, and then like that, okay. Actually this, if the numbering is proper, which is I think 1 3 5 2 6 4 or something like that, then you will see somewhere that this is 6 plus 1 and 1 plus 2 plus 2 plus 3 plus 4 4 plus 5, like that this conduction will happen if the numbering is proper, okay, exact in the same sequence. So this was the reason why we had this kind of a numbers on this one, but you can always write that this is D1, this is D2, this is D3, and this is D4, D5, and D6. You can also write down your diodes like that, numbered, okay. So basically the whole converter works with the 6 pair of conducting diodes, okay. At any point one diode from the positive group and one diode from the negative group, they are conducting, and the line voltages are appearing across the load. So since this is true, so we can now find out what is the average output voltage, right? So in order to find out this average output voltage, we have to see that this voltage is, this is the voltage which is coming across the load, and it is repetitive. Okay, there are 6 identical lobes, and so it is good enough for us to actually do the integration from pi by 6 to pi by 2. So this point here is basically pi by 6, and this point here is basically pi by 2. So it is enough for us to actually integrate from pi by 6 to pi by 2, right here. Now in this interval, which voltage waveform is getting followed? So if we go here, you see here the A, this is conducting, and here B is conducting. Okay, and so if we see here, during this point VAB is conducting. Okay, what is the equation of VAB? Okay, the equation of VAB, so assuming VA to be equal to VS sine omega t, then VAB will be root 3 VS sine omega t plus pi by 6. We know that the line voltage leads the phase voltage by 30 degrees. So that is why, and it has a magnitude of root 3 times. So VAB voltage will be root 3 Vs into sine omega t plus pi by 6. So this is the voltage which is appearing. So here the VAB voltage is appearing, and it is coming from pi by 6 to pi by 2, right? So therefore we just have to integrate in order to find out the V0 average. We have to get this 1 by pi by 3. So this duration is this duration here is pi by 3. Okay, so 1 by pi by 3, and integrating from pi by 6 to pi by 2, right? And root 3 Vs sine omega t plus pi by 6 and d of omega t, right? So basically this is the voltage which we are going to get the average of it. So you can substitute this omega t plus pi by 6 as beta. Okay, by substitution of variables, you can write this as sine beta d beta, where beta equal to omega t plus pi by 6, and then you can also integrate from we have to change the limits, okay, when you substitute the variable, and so we get pi by 3 to 2 pi by 3 and 1 by pi by 3. So when you do this one, this is pretty simple, you get this value, okay, 3 root 3 Vs by pi, which is 1.35 times the line voltage RMS, right? So this value earlier we had seen was the earlier value was 3 root 3 Vs by 2 pi, okay, in the half bridge half rectifier case. Now we have basically double the voltage here, okay. So V0 average is 3 root 3, so we get double voltage. So double voltage as compared to half bridge case, and that is the reason we, for any high power applications, we go with a full bridge rectifier arrangement. Okay. One thing that is also important to note, but we will not discuss it in details, is that the output harmonic analysis of the output voltage can be done, okay, if to design any output filter, okay. So if you do the harmonic analysis of this waveform, okay, what is this one? So the amplitude of the nth harmonic will be Vn is equal to this value, okay. You can do it yourself, you are not going to do that here, okay. So what it shows, that the harmonics, in the output, the harmonics are of the order of 6n, okay. So we have harmonics like 6th harmonic, 12th harmonic, 18th harmonic, like these harmonics being present in this waveform, okay. So you have 50 hertz if the fundamental, then 300 hertz, and then 600 hertz, like that, okay. So these harmonics will be all present at the output voltage waveform, and these will be useful if you want to suppress them, you have to design a filter, and when you design the filter, the harmonic content of the output voltage is important. Okay, so let us take a small example, okay, with a three-phase diode rectifier. There is a three-phase diode bridge rectifier, and it is the rectifier in supplying a resistive load, and this voltage is given. So this voltage, okay, when it is a three-phase system, this always means this is a line voltage, okay, and line RMS value. Okay, when nothing is specified, it is always meaning that it is a line voltage. So find the average output voltage and the peak-to-peak output voltage ripple. What is the average output voltage? As we have already seen, 3√3 Vs by pi. Okay, but note here that this Vs is the phase voltage amplitude. Okay, it is a per phase. Vs is the amplitude of the phase voltage. What is the phase voltage here? So phase voltage is, this is the line voltage, so this is line voltage here, and line by √3, so this is the phase voltage RMS value, and then you multiply by √2 so as to get the peak phase voltage, which is 338 volt in this case. Okay, so once you substitute this one here, then you get V0 average, V output average as 560 volt. Okay, what is the peak of this output voltage? As you can see, as you can recall from this one, this is the peak of the output voltage, right? Okay, so the peak of the output voltage is nothing but the peak of the line voltage, right? And therefore this is 415 into √2 is equal to 587, right? What is the minimum of the output voltage? The minimum of the output voltage, so this, if you see here, so this is the peak, right? And this duration is 60 degree, so this duration must be 30 degree, and it will follow a cosine waveform. Okay, so if this value is Vs, then this value will be Vs cos 30 degree, right? So Vs cos 30, because this is following a cosine wave here in this interval, so this is Vs cos 30 degree, which is equal to 0.866 Vs, right? So this is the minimum voltage. So therefore if you go here, so this is the 587 into cos 30 degree. Okay, so this value will be 508 volt. Okay, and hence peak to peak output voltage is this minus this here, and we'll get it to be 78.65 volt. Okay, so this is how we can get the values. So now the other part is with a constant current load. How does it work? Is that with a constant current load, again we can find out what is the input current. Okay, and so with a constant current load, again we can see that there will be always one pair of diode conducting. So here there will be, suppose this conducts and this conducts, suppose, okay, AC will be conducting. So there will be always, so for example here you can see this, during this interval A and C is conducting, B is not conducting, right? So the current goes through like this, comes like this, and goes back like this. Okay, so during this point, but since this is a constant current load, this I0 will come on the A phase, so this I0 will flow from here and it will go back through the IC here, right? So therefore we see that this waveform here is all quasi square, the source current waveform. So these are all source current. Okay, the current taken from the, so the grid is here, so the current is taken from the grid, and that current is all quasi square. Okay, and so they have 6 pairs of diode combination, and each is spanning 60 degree, and so we have a quasi square arrangement here, quasi square current waveform, which is coming from the source, and with a zero period, of course. So this is basically something which, again, I have told you many times now, is something which is not very welcomed by the grid. Okay, so the grid does not like this kind of a quasi square waveform, and this is a highly non-sinusoidal waveform, and will lead to very poor power quality and with a lot of input current harmonics, okay, and with poor power factor. So there are some standards like this standard IEEE 519 or IC 61000. They will not allow such a current to be taken from the grid, or in other way you cannot inject such a harmonic current into the grid from your converter or from your equipment, okay. So this is something which is not allowed as per the standard, and grids will follow this, and they will not allow you to connect your equipment if that equipment draws a current. So this is definitely not allowed. This type of current waveform not allowed by the grid, okay. So therefore we need to find some arrangement to improve this current. We would like this current to be like this, okay. We would like to be a sinusoidal current, okay. We have to change this current. So this we will see in the second week of this one, but we will in the next week we will cover on, or in the next lectures we will cover on the thyristor rectifier a little bit before we go into some of the strategies to make this current waveform closer to a sine wave. And so with this we conclude this diode rectifier part, and we will touch briefly on thyristor rectifier in the next lecture. Thank you.